So almost all microservices need some kind of data store to hold and persist the state of its information. For example, order service will need to store the incoming orders somewhere in some database. Payment service would need to store the incoming payments or the refunds that they are making into some database. Now here, the two databases where the orders is storing the orders or payments is storing the payments information could be same or different. The pattern we talk about today is database per service pattern, in which what we get is every service has its own database. Rather, every service has its own independent database which the service owns. This promotes something that we strive for in a good microservices based architecture, which is loose coupling. By having a service owning its own database, we are creating loose coupling between the two services, making them independent and autonomous. Independent to build, test, deploy and scale their applications. Autonomous to take the decision on their own database or any other peripheral decisions. For example, the communication, business logic, API contracts. But here we are putting our focus on database per se. So autonomous in making their own decisions for the database that they have. So if, for example, let's say we are building a social network. Social network is not just one small set of code base, it's gigantic code base. There are so many services that you would have to build in order to run or in order to have just one social network. For example, a chat service where there is a very high ingestion volume of information coming in, where people are chatting and everything needs to be stored and persisted. The chat service needs to have a database that is write heavy or that can handle a large amount of writes and should also be able to support a specific kind of reads. So that's where a partitioned NoSQL database like Apache Cassandra would be a very good choice for a chat microservice. For an authentication service, a simple relational model or a simple relational database with master and replica setup is good enough to handle a large amount of load. Or in case of a profile service, where let's say you have a very schema-less information about some information that a profile of a person might hold, it's not fully adhered to a particular schema. You might want to go for a non-relational database which is schema-less like a MongoDB, and in order to scale reads, you might want to configure it in a read replica setup, right? So that would give the best performance or extensibility for that particular use case. Another, for your analytics system, you might want to have a gigantic data warehouse. You would not want to fire your super complex analytics query onto your main transactional database. So that's where analytics query would need its own database, which would be its data warehouse like Amazon Redshift. Or if your social media supports videos, you have to store videos. You cannot store videos in your transactional DB. You might want to go for something like an AWS S3 or any kind of blob storage to hold that information. Right. So here we see how a simple looking social media that we use on a day-to-day basis has so many microservices, and each service has to take its own decision about its database so that it could give the best performance for itself. Like for chat to be performant with respect to, because that is a use case where it is read heavy and write heavy. More so than that, it's more write heavy than read heavy. Because of that, we need to have a database that supports very high write throughput. And hence it needs to be partitioned. You may not need partitions or you may not need sharding for authentication service or for profile service. But for chat, definitely yes. Right? Similarly, for video, you would not put into the same transactional DB, because why to do so? 2 GB of videos in one transactional DB, very bad design decision. That's why you would need a blob store and some meta information to be stored in some transactional DB. Analytics queries are very heavy. You do joins across 50-60 tables to get some information. Why would you want to fire that query into your main transactional system or into a shared database that would take down other services? So one bad query or one gigantic analytics to be done would take down your entire database. That's why having that separation of concerns or having that independence to take their own decisions paves a very good way to get the max performance out of your overall system. So now let's talk about advantages. Now that we understand the kind of decisions we would be making or the kind of things that we are signing up for, let's talk about the advantages of adopting database per service adopting the database per service pattern. The biggest advantage that we get is we create loosely coupled components. This is the heart and soul of microservices based architecture, where because of loose coupling, what we would definitely want is every service to run independently and like not just service but also the team owning that service should not be dependent on other teams. This promotes that. So for example, you have a recommendation service, you have a profile service. Because recommendation service has its own DB, profile service has its own DB, what we would get is for them to talk to each other, they would not get access to cross database. Like recommendation service might not have access to the database of the profile service, or profile service will not have access to recommendations DB. So that's where when the two services would have to talk to each other, instead of directly talking to the corresponding databases, they would have to talk to each other and talk via API contracts. This way, any changes that can happen onto a database will keep the service unaffected. And you can very easily scale out this system. Now, tomorrow if we have another service who needs the same profile information, could just talk to profile service rather than sharing the same database or doing that part. And now each of the service will have its own team to build and develop and whatnot. Right? So you get loosely coupled components. That's the heart and soul of microservices based architecture through this database per service pattern. Second is you have a very specific need. For example, in order to model relations on social network, for example, A follows B or A is friends with B, you might want to go for something like a graph database. Let's say we are building LinkedIn and on that you see two people, A and B, are connected or not, or how far are they? Is it one order connection or basically the second order connection or the third order connection, right? So how far are they? This could be very well modeled. Not saying that they have modeled it this way, but this could be modeled on a graph database like Neo4j, Amazon Neptune, dgraph, whatnot. You can model it there. So if you are modeling something like a social network or social relationship on a network, you might want to go for graph database because you need those algorithms. You might not want, or if you do it on a relational DB, it would be very inefficient to do so. So that's where, in order to fulfill the specific need of a particular use case of your application, you would want to go for a specialized database. A small example to conclude on this point would be to power a full text search engine, you might want to go for Elasticsearch. So that, because that's meant for that particular use case, why would you want to do it on a relational database using like queries, right? Very poor way to design that. So that's where, in order to fulfill the specific need of a specific service or a specific use case, you would want it to be as isolated as possible and as autonomous as possible. Next point is you want to have granular control of scaling your service. Database is that one component that is super important for scaling. Like if your database scales, your service scales, because the scaling of API servers is pretty much sorted. Like you put it behind load balancer, add an auto scaling group, and that is sorted. But scaling your database is tricky because your databases are not elastic. Like you cannot just say, hey, increase the size of my database and it would happen in 2 seconds. It takes time, right? So that's a very infrequent activity that you would do. So that's where you would want a very granular control of scaling. First of all, to keep the cost in check. Second of all, to take the best decision for your infra. For example, in case of a chat system, a partitioned way of scaling is good for write ingestion or a write heavy system. That's where you might want to have a partitioned database. On the other hand, where you are building something like a payment service, you might want to go for a very strong ACID compliant database like MySQL or Postgres, so that your data never goes in an inconsistent state. The scaling for both of these databases are totally different. Scaling for system like chat, you could add read replicas, or you could, to handle writes, you would want to go for partitions. For scaling payments, you might want to go for vertical scaling because you want a very consistent view of data. So that is where you can pick any of the scaling strategy for your use case. It could be horizontal, vertical, replica, basically read replicas to scale reads, partition, or decentralized. It's all up to you, right? So that's where for your specific service, for your specific use case, you would want to pick, or you should be picking the best scaling strategy that would keep the cost in check. Next is if your database goes down, when you have data, and in most cases, most outages that happen in the world are either due to DNS or due to database. So because it's, in most cases it is due to database, or your database choking, or your database is under heavy load, or it went into a reboot state, something happened with your data. In most cases it is always the database that is the root cause of all evil, and chances of that going down is very high. When your database goes down, it takes everybody with it. Imagine having a common database for your entire social network. What would happen? If that database goes down, your entire site is down. So that is where what we can see is, if we have database per service architecture, if a particular database is down, then only the services dependent on those databases, directly or indirectly, will be affected. For example, if a profile database is down, then your profile service is definitely affected, and any service which is dependent on profile service synchronously will be affected. On the other hand, if your payment service never depends on profile service, then your payments is working fine, you are getting revenue and you are happy, because even if your website is down or your profile service is down, you are still accepting payments, you are not losing out on revenue. Next is you have a separate compliance need for a certain type of data. See, this is something that if you are a senior engineer, you would have definitely seen it. If you are not a senior engineer, you would see when you turn a senior engineer. Compliance, something that you have to worry so much about, that hey, I am storing PII information of data. PII is basically personal identifiable information, like your email, Aadhaar card, or your social security number, and so on and so forth. Your PII's information is very critical. So, for example, if you are storing a critical information, like let's say financial data or payments, you might want to have a policy where you would want to encrypt the data at rest, which means that while you are storing the data in your database, it should be stored in an encrypted way. Or the disk on which your database is stored, that should be encrypted, and so on and so forth. So there are multiple or there are many checks that you would have to put in, or many things that you would have to adhere to when you're dealing with data that has some global compliance applied on top of it. Now here what would happen is, if you have database per service architecture, you would only need to encrypt that database or that table. And like, for example, if your entire data size is 2 terabyte, but your PII information or your financial information only comes in 10 GB, encrypting 10 GB is much simpler as compared to encrypting 2 terabytes. And it's not just one-time encryption. Every time when you're inserting, you have to encrypt it and whatnot. Your database implicitly has to do it. And that would impact the response time of your services, given that you would be encrypting on every call and decrypting while you are retrieving it every single time. So that is where, for a separate compliance need, it is always better to keep your database granular, so that you can put those necessary checks only on those databases and not touch upon any other. Right? So these are the advantages of having database per service architecture. The second the things that we conclude with today is looking at disadvantage. Obviously, again, as I always say, grass is not always green. We have to look at disadvantages of going for database per service architecture. It's not just that because of this we would not be adopting it. Obviously, hybrid approach always works, but we should know what we are signing up for. Right? First disadvantage is your cross-service transactions are super complex and super expensive. I cannot add more super to that. It's very complex and very expensive. So cross-service transactions, for example, if you are building, let's say, a 10-minute grocery delivery system. I have a video on actual implementing distributed transaction. But let's say if you are building a 10-minute grocery delivery system, and hypothetically you only want to accept the order when you have the inventory and you have a delivery person available. Inventory has its own database, is its own microservice. Logistics has its own database and is its own microservice. So now what would happen is, when the request comes to your order service would have to place an order only when you have an inventory, and you have a delivery partner to deliver it. This is a classic case of distributed transaction. Now, in order to implement distributed transaction, you have to implement either a two-phase commit protocol or some way to implement distributed transaction. And because it is distributed, it's prone to failures, network outages, and whatnot. And it takes time for you to even converge upon a distributed transaction. It's not as simple as you start begin transaction and end transaction like you do in your relational database. So that is where implementation is complex and expensive. Expensive with respect to time and throughput. As soon as you add a distributed transaction, you are slowing down your throughput by at least 3x. At least 3x you are actually slowing it down. Because it is that slow to implement. Because there are a lot of distributed components that come into the picture, and it takes time for you to guarantee consistency and whatnot as part of distributed transaction. So I would highly recommend you check that out on my channel or on my website. Implementing distributed transaction using two-phase commit, where I've actually implemented that. And you'd realize that distributed transactions are not just theoretical, you can actually physically implement those things, and I would highly encourage you to check that out. Okay. Second disadvantage is not disadvantage, but a little hiccup, where conveying updates across services is difficult. Like for example, if the two services would have shared the database, they can directly talk to the database and see the latest state of it, right? But here, let's say you are building social network and you have a post service on which whenever user posts something, that comes to this service and it has its own database where it is persisting. And then you have a feed service. In the feed service, you are generating the feed of a user. Now what would happen is anytime a new post is created, you have to trigger the feed service, or you have to let the feed service know about that newly created post so that your feed service can put it into the feed of your followers. Right? Now, how would this communication happen? So this update flowing typically happens through a message broker, mostly an asynchronous system. Message broker like Amazon SQS, Kafka, RabbitMQ, or basically even Redis as a message broker. Pick your favorite. But the idea here is from post service to feed service, some way you have to flow the updates, right? So you have to convey the update. That's a little complex, although it's not really hard, but you have to be wary of the fact that it will take some indeterministic amount of time for the update to come out of your post and reach your feed. It will not be strongly consistent. It will always be eventually consistent. And the final drawback, which your SRE team or your DevOps team would very heavily relate to, is multiple infra components to be monitored and managed. Now that imagine you have different flavors of database, like graph database, NoSQL database, or key value store, document store, columnar, warehouses, whatnot, or graph database, right? Your teams need to, your SRE team, or even in your case, if you are managing it, you need to have those expertise into, first of all, writing efficient queries. Second, observing what's happening on the infrastructure. Third, knowing how to scale it without any downtime. Fourth, in case of a downtime, how to mitigate it. Small things, it adds up a lot of things. So you need to have that knowledge to manage the database, monitor it, and it's not very trivial. So which is where this, for an engineering leader, this becomes the biggest concern. Apart from all the technical challenges that are there, this is the biggest concern for any engineering leader. Oh my God, I have to manage more systems, and it's not at all straightforward. So that's why you would see whenever a new technology is being adopted, a lot of teams have concerns about it. It's not that they don't want to change, but it's more like managing them, or they might not have enough confidence in managing them, or they would need time to build that sort of expertise in managing it. So that's the harsh truth of our industry, but that's how the industry works. So these are disadvantages / concerns about database per service architecture, and I hope it was pretty exhaustive per se. I tried to give you a little bit of insights around everything on how those things happen and how we function. So now you understand database per service architecture, advantages of it, disadvantages of it, modeling a social network, different kinds of databases. We just touched upon it a few times. Understanding how it promotes loose coupling, autonomous and independence. right? So yeah, that's it for this one. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks, Atar.